Okay, we're starting lecture 1 with describing sets and operations on them. So what is a set? Well, a set is just a collection of objects, which in our settings, most of the time, those objects will be numbers. And those objects inside the sets will be called elements of the set or members of the set. And usually we always start and end the set with curly braces, and very often we separate elements of the set with commas. So for example, if I want to set the set A is the set, so A equals the set containing 3 elements, 1, 2, 3, and then I end the set with the curly braces. Okay, so that set just is a set that has 3 elements in it. Now we will discuss 3 operations on sets: union, intersection, and complement. And for me to discuss that, we have to put our sets in the context of the universal set. So universal set is kind of like everything that there is, right, in this context. So for example, we can say that universe is the set of all natural numbers up to, say, 10. Okay, what that would mean then, that whatever sets we're going to create, they can only contain those elements from 1 to 10, because this is our entire universe, right? And why do we need the universe? Well, mainly for the complement operation, and we'll get to it more once we're gonna describe that. But let's first start with the union of 2 sets. So how to take a union of 2 sets, and notice this is indicated by this kind of white U-looking symbol, right? Union. So a union is the set that contains an elements that either belong to A or B. And that my description might be confusing, but how I would like you to visualize this is that the union is kind of like this bucket that to which you throw all the elements from set A or B. Well, so basically it means that if you were to pull randomly an element from this bucket, it's either would belong to previously to A or to B, okay? Or maybe to both if that was the common element, right? That's what it means. Another way of saying, if you were we're looking at the file system on your computer, think of A as a folder and B as a folder containing files. So if you were to take a union of those 2 folders, if you were to merge those 2 folders together, right? So you create a new folder that contains all the files previously in folder A and B. Okay, so this is so-called Venn diagram, and those is good to put in the context of the universe. So universe is everything there is. Okay, so union would just be those 2 sets combined, right? Now intersection, I think that's kind of is probably intuitively more clear, which we denote by the upside down U. So A here, intersection B, is the set that contains elements such that they belong to both A and B. So basically intersection is the set to which we throw the elements that A and B have in common. And this in Venn diagram would look like this, right? So the shaded region where the 2 sets overlap, is kind of their common piece, right? And we're going to do some problem 1 in a minute to explain it a little bit more. And then a complement of a set A is basically everything that's not in A. Everything that's, of course, in the universe, but not in A. So let me quickly here draw a Venn diagram. There's none for the complement. If this were to be a universe and then we get the set A, then complement of the set A would be just everything outside that set. So we take all the elements from the universe that do not belong to A. So all the elements kind of outside the set A. Okay. Okay, so let's look at the problem here. So we have our universe set. So those are the only elements we can work with, right? So we have 0, 1, 2, 3, 4, 5, 6, 7, 8. So the universe is the set containing those 9 elements from 0 to 8. Now A is a set that has elements 1, 3, 5, and 6. B is a set that has those elements 3, 4, 5, and 7, and so on, right? And C is this. So let's find A union B. Well, so A union B, the union of two sets is a set. So let's remember to start and end with curly braces. And then what do? We just take combined A and B, right? So we throw those two content of those two sets into one set without repeating the same element twice. So because we think of it as exact same element. So 1, 3, 5, 4, sorry, 1, 3, 4, I'm gonna organize them from the smallest to the biggest, 5, 6, 7, right? So I threw one element, I grabbed it from A, 3 actually in both, then 4 was from B, 5 from A, 6 from A, 5 also from B, but I didn't repeat it twice, and 7 from B, right? So basically, you threw all the elements from A and B into one set. Okay, A intersection B. Okay, what is A intersection B? Is the set to which we put common elements of the set A and B. And what those two sets share in common? Well, 3, like we noted before, and 5. Those are common elements, right? So intersection will be the set that has those two elements in them, right? The elements that two share in common. Okay, let's look at A intersection B in parentheses, union C. So same as with the operations on numbers, if you see grouping symbols, you do those first. So they kind of establish the order. Do first A intersection B. Well, and we happen to do that above, so I'm just going to rewrite it, union. And then we're going to have to take a union with the set C, and I'm going to spell out what the set C is. Right, so A intersection B, we did it first, and we did it above, so I just repeated 3, 5. And then union with the set C, which is 1, 5, 7. So let's put all those elements into a single set, and I'm going to list from the smallest to the biggest. So 1, right, that came from the set C, then 3, 5, and 7, right? Because they share 5, so I haven't repeated it twice. It's still the same element. And then I see elements 1, 3, 5, and 7. Okay, let's do complement of A. So it will be a set. So if you look at the set A, it has 1, 3, 5, 6. So imagine those 1, 3, 5, and 6 removing from your universal set. And then, so then A complement will list all the remaining elements. Because remember, what's the complement of A? That everything that's in the universe, but not in A. Basically, everything outside of A. So we cannot, we have to basically exclude the elements that belong to A. So we cannot take 1, 3, 5, and 6. Okay. And finally, A complement intersection B. So let complement, we know, we have it above. I'm just going to rewrite it so sometimes it's easy to exactly write those two sets to see them side by side. Okay, so 0, 2, 4, 7, 8, 3, 4, 5, 7. Remember, intersection, this upside down U means what they share in common. So I'm going to highlight what I see they do have in common. So they have 4, right, and 7. So that would be the set that has those two common elements in it. Now let's look at graphing inequalities. So we're going to often work with some kind of sets that are described by inequalities. Because whenever you see an inequality, like for example this one, then that doesn't represent just one number, but the entire collection of numbers that satisfy this inequality. One thing also I want to mention is that we're seeing that I want to remind you that inequality symbol always open towards the bigger number. So if I write A and B here, then remember B is bigger because this inequality symbol opens towards it, right? So B is bigger. So always inequality symbol opens in the direction of the bigger number. Sometimes you might see, and we call this inequality strict, but if you have or equal, like something like this, we call it this inequality non-strict. So that says here, if I wrote now this way, that would be A. B is still bigger or equal to A. Or of course you can read A smaller or equal to B. Both mean the same thing, okay? And I want you to be able to draw the inequality. So here, first let's establish what that stands for. I see that always think, which one is bigger? 3, right? Because inequality symbol opens towards it. So you would read, since you want to read it in the context of x, what x satisfies, you would read x smaller or less than 3, right? So we have x is less than 3. So how to draw it? Well, you draw the number, and it doesn't matter, somewhere on the number line, you draw 3, right? You don't have to draw anything else. And then all you need to establish whether your your x's, because it's just not one number, but the collection of numbers, whether your x's are to the left of it or to the right of it. Since we said that x is less than 3, then of course that means to the left of the number. So I would highlight, and then you have many options how to do it, of course. We can sometimes mark exactly on the number line. I'm going to do it above to make it just a little bit more clear. So here we put, whenever inequality is strict, we put an open circle, and then to the left will indicate with the arrow, okay? So that would be, maybe I'm going to do it in red. This would be the graph of this inequality. And last thing I just want to point, we're done, but last thing I want to point is that sometimes in some textbooks, instead of open circle, we would put the open parentheses. That basically means that the 3 is not part of the solution. We're here taking everything that's strictly less than 3, but not 3 itself. So that's what the open circle represents, and that's what's in some textbooks open parentheses stands for, right? So if you were to write it as an inequality, we always read inequalities from the intervals from the left to right, like we read words. So you would say since that never ends, so that's from negative infinity to 3, okay? Okay, so let's do the next one. So two numbers that you have to mark are -1 and 4, and then you have to figure it out in reference to those numbers where x lies, right? So if we call it compound inequality because it's like two inequalities in one, really. This one first, if you just look at -1 and x, inequality sign opens towards x, right? So it says x is bigger than -1. But if you focus on the other one, it says x is less than 4, because then 4 is bigger, x is smaller, right? So basically x is bigger than -1 and smaller than 4. at the same time. So bigger than -1 is to the right, but smaller than 4, so I cannot go past 4. So again, either this or here parentheses, depending what this book is using. And basically, so the interval, if you were to write it as an interval, it will be just from -1 to 4. That means everything in between the two. Because we read from the left to the right. And D is very similar. Again, you have compound inequality. X is bigger or equal to -2. This is or equal, right? Here, so X is bigger or equal to -2 and less than 3. So two numbers I need to mark is -2 and 3. Now, bigger or equal to -2 means to the right, and less than 3, I cannot pass 3. Now that here, if it's less or equal, you put closed circle. When the inequality is strict, you put open circle or bracket and parentheses. Again, I haven't checked what notation this book uses. Okay? Bracket and parentheses are a little bit easier than to write it as an interval because it's exactly how you would write it, from -2 to 3. Okay. So let's move on. I hope that we kind of reviewed the inequalities, how to read them and how to write them or draw them. Let's look at expressions and mainly their domains. I'm going to do just B and D. So with B, here is evaluate the following expression if possible, if X is 2 and Y is -4. So basically evaluating expression, we're going to do a lot of evaluating expressions. Is simple because all you do is just evaluating means plugging in numbers for those variables, right? So for X, we plug in 2, and for Y, we plug in -4. And then we evaluate. I just want to remind you order of operations. You first do everything within the grouping symbols, within parentheses, brackets, but we don't have any. Next, you do exponents. We don't have any. Then you do multiplications and divisions, which we do. So we first have to multiply before we can add, right? So 4 times -4 is -16. So we could have written that as 4 minus 16, not 4 plus -16, the same thing. And that's going to be -12. And then I'm going to do, guys, D. So let's evaluate at X equal 2 and Y equal -4. So what would I have to say if I have 7 over 0? Undefined, right? I just wanted to remind you that we cannot divide by 0. But also another purpose of giving you this example is that with rational expressions, and that's a rational expression when you have a fraction and some polynomial on top and some polynomial on the bottom. With rational expressions, there are things that do not belong to their domains, things for which the rational expression might not be defined. In this case, Y equal -4 is something that cannot be plugged in, right, to the expression. So that would be something that's not in the domain of your rational function, but everything else would work, just not -4. So let's determine the values of X that need to be excluded from the domain of this expression. So if you look at the X minus 4 divided by X, the A, what X cannot be equal to? What number, if I were to plug in for X, would create division by 0? 0, right? Because think what that number would have to be. If I plug in for X 0, the top doesn't matter because top can be 0 or it doesn't have to be 0. What I focus on just to make sure that I will not create 0 on the bottom. So X cannot be 0, right? If it was, then I end up dividing by 0. So I'm going to write x has to be different than 0, or the value that has to be excluded from the domain is 0. How about the b? What x cannot be equal there? 4, right? Because again, you only look at the bottom. What number, if I were to plug in for x, would end up dividing by 0? So if x was to be 4, 4 minus 4 is 0, right? And that's not allowed. So x has to be different than 4. So I'm building some, I know that a lot of you know it. I'm just building some stuff we're gonna use all the time just to set up our proper base. Now we're gonna talk about rules of exponents. Again, this is all review. You had it in college algebra, you had it before. I just want to remind you that this rule, which is also can be expressed in as this rule, it's kind of like really the same version of the same rule. What they tell you is, if you look from the right side, that the exponents can be distributed among products and quotients. So if you have a product that you need to raise to a power, then you can raise to the power each factor of the product separately, okay? Immediately, I always emphasize that because a lot of even advanced students make that mistake, that if you have a sum, then that would be incorrect, meaning you cannot distribute the exponent or the power among the sum or difference. Okay? It's not, this is not equal. I can give you many examples for which that's not going to be the case. So basically, if you had here, if you change that to multiplication, then yes, you can distribute the power. Or if you change that to division, then yes, but not if you have a sum or a difference, right? And I'm gonna tell you that many times this course, just to remind you, because this is the common mistake, right? So, but first rule just says you can distribute the power among the product, right? Or pull it outside the product, like depending from which side you read it, right? Now I'm gonna move on to the third one here. If you have one power after another, it becomes a product of the powers. Why is it so? Let me give you examples. Say 5, you'll see it very quickly. 5 cubed to the square, okay? So what do we need to do with that's gonna be 5 to what power? According to that rule, should be 5 to the power 6. You should multiply the powers, not add. Why is it so if you wanted to kind of test it? Okay, what's 5 to the power 3? 5 times 5 times 5. Right? And what's now that to the power 2? Well, that 5 times 5 times 5, I have to multiply by itself. 5 times 5 times 5, right? So when you look at this, what you have, this times this. So I multiplied the same base, 5 times 5 times 5, twice, right? This times this. So basically I have twice 3 factors of 5, meaning I have 6 factors of 5 combined. When you analyze that, it makes sense. But of course, when we do all sorts of simplifications of expressions, we just have to know the rules, okay? So one power after another, so one base, just 2 different powers kind of touching each other, then you have to multiply them. But what happens if you have the same base showing up twice? Notice the difference. 5 cubed times 5 squared. So let's analyze that. What is 5 cubed? 5 times 5 times 5, right? What is 5 squared? 5 times 5. So basically, combine how many 5s, how many factors of 5 do I have? 5. So that's 5 to the power 5. So what we had to do now with the powers, we had to add them. Because all you need to really do is think, okay, how many total factors of 5 do I have, right? The first power told me I had 3 factors of 5. This told me I had 2 factors of 5, so combined I have 5 factors of 5. So the last rule, this one, is the one I just discussed. If you have the same base with different powers, then you're gonna add the powers when you multiply them, okay? Okay, but now one more thing, which is this rule is not listed, but it really combined with the rule above, will give you one more rule. I want to talk about what negative powers represent, to remind you. Negative powers just tell you, say 5 to the power negative 2, just tell you that this 5 squared really belongs in the denominator. Okay. Okay, if you were to even let me do something like this. I always teach that to my students. That if you have a negative power within a fraction, you can always take its reciprocal, which essentially brings them to the other side of the fraction bar, and that gets rid of the minus then, okay? Because negative power stands for the reciprocal. So if you want to get rid of the negative power, then bring that thing that has negative power across the fraction bar. What had positive power stays where it was. So that now will be 3 to the power positive 1 on top. So that's kind of extension of this rule, but useful a lot if you're dealing with fractions, right? So negative power means reciprocal. And in the context of having a lot of factors with negative powers within a fraction, it's a cool trick to kind of shift them around the fraction bar, which gets rid of the minus. We're going to do exercises. So with this in mind, if what happens when you have division, 5 to the power 7 over 5 to the power 3, let's do something like that. So notice I have the same base, but I'm not multiplying, but dividing the expressions of the same base. So you can really visualize it, that what will happen is, you can even draw it. This would have 7 factors of 5. This has 3 factors of 5. So really 3 factors of 5 cancel 3 factors of 5 from the top. So you only end up with 4 factors of 5. So what do you need to do with the powers? You have to subtract, because the factors in the denominator take away that many factors from the numerator. So you're going to have to subtract the powers. Okay. So a lot of rules, important ones, they're going to show up in this course quite a bit. You're going to see them. What do you think, guys? Are we ready for examples? So we're going to do examples now, utilizing all those rules. But if you have any questions or something is not clear, let me know. Or even if you have a question, why would I know to do it this way or not the other? Sometimes there are many ways to solve the same thing. So x cubed y to the power negative 2 and times z. Notice there's nothing in between. That means that we have products here. I can always put this multiplication dot just to remind myself we're talking about product, right? So x cubed times y to the power negative 2 times z divided. So you have a fraction bar, x to the power negative 2 times y. Okay. So now there are many ways, but I don't like to have negative powers within fraction because it's easy to make mistakes with negative powers. So I would suggest to do what I show you, this trick of rearranging. So what has positive power stays where it was. So x cubed stays on top of the fraction bar, and z will stay where it was on top of the fraction bar. But y to the power negative 2, I'm going to bring down, which will then become y to the power positive 2, right? So basically, by bringing it across the fraction bar, I get rid of the minus. So that y to the power negative 2 is now y to the power positive 2 on the bottom. This y, since it has positive power, stays where it was, okay? So I'm going to mark in yellow things that stayed where they were in the fraction bar. But now x to the power negative 2 from the bottom is being moved to the top, and that becomes x to the positive 2. So think about it a little bit, what we did. What had positive power stays where it was, and with negative powers, expressions were pushed across the fraction bar, right? And now all the powers are positive. Makes sense, the first step? Okay, so now, serious, I'm going to answer smart questions. Okay. So what do we do next? Well, if we have base-like expressions like the same base x, we will combine it, right? So how many total factors of x do I have? X to the power 5. Because remember what we do, we add the powers, right? Always when in doubt, think about it like x times x times x, the other is x times x, and count how many factors of x you have, right? But if you multiply base-like expressions, you're adding the powers. Well, z, there's nothing to do with z. And then there is on the bottom y cubed, because again, this is like y to the power 1. So I can add the powers, or you can really visualize it that that's y cubed, right? 3 factors of y. Okay, so that's what I suggest to do. But the B, we're going to proceed the same way, but notice there is an extra here obstacle that we have parentheses, grouping symbols. So I would want you to always think, if you're planning to simplify expression, first attempt to get rid of the grouping symbols, get rid of parentheses. That might mean different things depending on your problem. But in this case, what does it mean getting rid of the grouping symbol? Distributing the power among each factor in the product. Because remember, powers can be distributed among products or quotients. Right? So that will be x squared. This will be now y to the power negative 2 and z to the power negative 2. Notice it's all multiplication, right? If you don't see any operation listed, it means it's multiplication. So that was the first step. So what I did, again, I wanted to get rid of the grouping symbol parentheses. So I distribute this spot, people show up, and I think it's not the right class. It's the second person. So, or maybe it is the right, they just decided they don't want to be part of it. Either way, happened twice. Okay, so this is the first step. Now, what do we do next, guys? This rearrangements to get rid of the negative powers, right? What has negative power? What doesn't have a negative power will stay on the side of the fraction bar where it was. So actually, the only thing where it stays where it was is going to be x squared, but everything else will be rearranged. So let's be careful about it. First, I'm going to bring x to the power negative 2 on top, which will then become x to the power positive 2. It's all products, so with all products like before. So I brought this. Then, actually here, guys, let's say what we, z to the power negative 2, we can cancel, right? It's the same thing. So let's, if we rearrange that, it would cancel next step. But let's cancel that, so that makes it now easier. So now only y to the power negative 2 will jump to the other side of the fraction bar with positive power. And I'm almost there. The only thing I need to do is to combine x's. So I add powers because I'm counting total numbers of bases x, factors x. So x to the power 4 over y squared, that's the final answer. Okay, what do you think so far? Easy, right? Which I hope you're gonna feel that way about every lecture, okay? That's my really dream for this course, that you see it and you say, okay, it makes sense. Because really math, if you see it, you know what to do, it's really not that bad. All right, so let's do it C. So remember, the goal is to simplify this expression. And by simplifying, they specify that I didn't read the problem correctly. They say, leave the answers without negative powers and so on. But the first thing I will do is I'm gonna get rid of the grouping symbols of those parentheses I see. That's always my first attempt. So what do I know? I can distribute the outer power among products and quotients, right? So I'm gonna do it with 2 steps, but you can really do it in one. So what I mean by that, first I'm gonna raise the numerator to that power -2 separately and the denominator. So that outer power -2 has been distributed in this quotient. But then someone could have done within this one step what I will do next. But then on top, there is a product which allows me then to distribute this power among each factor of the product. Right? I can distribute powers among products and quotients, but not sums or differences. So x needs to be raised to the power -2, y to the power -2 needs to be raised to the power -2, and z needs to be raised to all of those have to be raised, right? Same on the bottom. Z to the power -2 needs to be raised to the power -2, and y cubed needs to be raised to the power -2. Okay, it kind of seems like we're still not done with getting rid of the grouping symbols, which is my first goal, right? But I'm one step away. Now, what do I do when I have one power after another? You multiply the powers, right? That was the rule. So we're gonna have to multiply those powers, and that will automatically achieve the goal I wanted. Get rid of the grouping symbol. So that would be y to the power 4 because we multiply the power. This will be z to the power +4 because we multiply the powers. And then y to the power -6, again, because we multiply the powers. Right? And then we're back to what we should know by now what to do. Like previous examples, what has positive power, which I'm going to mark just for myself to keep track, stays where it was, but everything else will has negative power, so I will try to rearrange it. So y to the power 4 stays where it was. Then I will add to it y to the power 6 because I brought it from the bottom. Then z to the power 4 stays where it was, but then z to the power -2 will become z to the power +2 on the bottom and x squared. And that now brings me to the last step. If I have base-like expressions, I can combine and count total number of y's I have is 4 plus 6. You're adding them because you want to have total count for the base y and in the product. And here you're also adding powers. So that's going to be z to the power 6 to see how many factors of z I have combined, and x, and this is the most simplified form. Okay. So hopefully it seems easy, but remember the rules I want you to, and that applies to any form of simplification. Get rid of the grouping symbols, parentheses, which for powers might mean distributing the powers among quotients and products, and then multiplying powers. Get rid of the grouping symbols, deal with negative powers by bringing them across the fraction bar, and then combine base-like expression by adding the powers. And all the problems of this type will boil down to that. Okay. So let's go down to polynomials. What do I have to say here? Okay. So polynomials are sums of the terms of the form constant times x to a natural power, okay? Like the example A here. Now you can always list terms of the polynomial by just, if you here separated those by commas, you would see all the terms. X to the power 4, -2x squared, x, and 3. Those are all the terms. Okay. Now, coefficients of the polynomial are the numbers standing by the x's to the power. So here, if you don't see the number, then you know that number is really 1. So the first coefficient for the first term is 1. The second is -2. Then we have 1, and then we have 3, right? For those terms corresponding to the terms above. But the most important term is the leading term, the one with the highest power of x. That leading term has a leading coefficient, is the leading coefficient. So that's a leading coefficient. That's the coefficient in the kind of leading term. And the power is your degree. So the highest power of x is your degree. So the degree is 4. All right, but I didn't even read the question what we're supposed to do. I just wanted to remind you all the terms that we're going to use. And here is determine whether the expression given is a polynomial or not. If it is a monomial, state this fact as well. Monomial is a polynomial that has only one term. Binomial is the one that has 2 terms, and trinomial is one that has 3 terms. And basically, we don't use above trinomials. We just, that's it. Okay, so this was a polynomial, right? And we actually listed all its terms, degree, leading coefficient, and so on. What about B? Is this a polynomial? I tricked you. Is it kind of, what if I added this? Would you think that's a polynomial? Yes. So this is still a polynomial, but a special one called monomial, because it only has 1 term. So it's kind of, we always think of polynomial like having a sum of terms, right? But if there's only 1 term, it's still a polynomial. It's just called a monomial. So yes, it is a polynomial. It's monomial. Okay, so a special polynomial with just 1 term. Okay, what about C? Is this C a polynomial? So you see x squared plus 3 square root of x. Use your intuition, what that tells you. Something stands out. Are you alarmed by something? Does it look like a polynomial? Okay, some people say yes. Anyone doesn't like something about this? We're not supposed to have square roots. Like polynomial is you only can have natural power of x, so x to the power 1, to the power 2, to the power 3. You're not supposed to see roots, because roots, I'll remind you that we didn't discuss it yet, but roots, square root, I can write as the power 1/2. And polynomials are not supposed to have fractional powers. You can only have power 1, 2, 3, 4, 5, and so on, right? Natural powers. So that's not a polynomial because of the square root. So what I want you to focus on to establish if something is a polynomial is really what matters is the power of x. There is no restriction on coefficients. That can be any number, but powers of x can only be natural, okay? So if you look at D, is that a polynomial? What is the power of, there's a x squared term and there's a constant term, right? So to me, it is a polynomial. Power of x's are the ones I want to see. I don't see any negative powers. I don't see any fractional powers. Only all the powers of x are natural numbers. So this is a polynomial. The fact that coefficient by standing by x squared is pi is an irrational number. It's fine. You can have any coefficient standing by x squared. Okay? So this is a polynomial. How about E4? Is it a polynomial? Yes, it's a polynomial which is called monomial. Something that I know honestly it doesn't matter whether you knew it or not, because nobody would call a number a polynomial, but technically it is a polynomial, because as long as you remember you don't see negative or fractional powers of x, so you see some sum of terms, or in some special case only 1 term, it's a polynomial. So this is a polynomial with only 1 term, which would be then called monomial. And in this case, the only 1 term that you see is a constant term, okay? So this is very exceptional, special polynomial, but nevertheless still a polynomial, okay? So polynomial. I'm going to write with only one constant term. Okay, let's look at x. When in doubt, you can always write x with the power. So here I can write x squared plus 9. That's a coefficient. And since x is on the bottom, it means power -1. Remember, I can bring x from the bottom to the top of the fraction, but then I have to change the sign of the power, right? So now it's going to be x to the power -1. So is it a polynomial? No, right? Because we're not allowed to have, I saw you guys nodding, letting me know it's not, because the power is negative and you only can have natural powers. So not a polynomial. Okay, this one is a polynomial. I'm gonna just speed it up, and that one is not, because of the 1/4 fractional power. Okay, I'm gonna skip A. I assume we, honestly, I feel like we all know it, but B will demonstrate example A well, and then we're gonna do C and D. So here, notice that this first lecture is just going through like 1 month of college algebra or something like that. We're going now through operations and polynomials. But I think that B is pretty easy. You all know how to do it. One thing I want to point out that basically, again, to simplify an expression, think about getting rid or dropping the parentheses. And in case of the polynomials, you can drop the parentheses unless you have a number or a sign in front of it, which in that case, you will have to distribute that number or a sign among all the terms, right? So when I look at the first parentheses, I can just drop them because there is no number or no sign to distribute there. But if I look at the other, then if I want to drop it, I can do it, but I have to distribute this minus that's in front, because minus, think of it as the same as a number, -1. So minus or a number needs to be distributed among all terms. So now to subtract that polynomial, I have to write minus 2x squared minus x and plus 1, because I need to distribute the minus. Okay, and of course, with polynomials, we then can combine like terms. And so I have 2x squared terms. And combining means that I really just subtract or add coefficients, right? So 1/2 minus 2, that's the operation I have to do. And whatever that is, that's going to be my coefficient by x squared. So what's 1/2 minus 2? -1.5 or -3/2, right? Because 1/2 minus 2 is the same as from 2 subtracting 1/2, but keeping the sign as negative because sign carries from the bigger number, right? So 2 minus 1/2 would be 1.5, and the sign is negative. That's coefficient that will have to stand by x squared. Okay, then x, -2x minus x. Well, that's, you don't see coefficient that's minus 1x. So -2 minus 1 will be -3x. So you combine, you add coefficients -2 and -1. And then 1 plus 1 will be 2. Okay, those are basics. Are we good, guys? So far, so good? So let's look about FOILing, multiplying two polynomials. And here we're multiplying two binomials, polynomials with just 2 terms. So how to multiply? Well, you know the FOIL method, which some might apply, but I like to, because sometimes if you have more than 2 terms, the FOIL doesn't apply anymore, but the FOIL method simply tells you to proceed this way. And the first polynomial, you focus on the first term and you distribute that one among both terms of the other polynomial. So x times x and x times 3. So that's going to be x squared plus 3x. Once you're done with this one, then you move on to the next, in this case, -1, the next term, and you do the same. You distribute this multiplication among all the terms from the second. So negative 1 times x and negative 1 times positive 3. So negative 1 times x will be negative x and minus 3. And the last step, you combine like terms. We have x terms, and you have it. All right, I'm going to focus on D, and I'm going to probably spend more time than necessary, but I want to make sure that you avoid this mistake. So some of you, and I still have it on exams, some of you think, okay, it's just 3x squared and 1 squared. So some of you might say something like that. 3x needs to be squared and 1 needs to be squared, right? If you thought that way, then you would be wrong. Because remember, outer powers, like in this case 2, can only be distributed among products and quotients, not differences or sums, okay? So here's the difference. So you cannot raise to the power 2, 3x, and 1 and just subtract them. Basically, you cannot distribute that power. So that's incorrect. What you should do, you should understand that's what power 2 stands for. That base 3x minus 1 needs to be multiplied twice by itself, right? This is really what means squaring 3x minus 1. There is a formula for squaring the difference, which I'll let you know in a minute. But I know there's a lot of students just don't like it and they prefer to FOIL. So I would advise you to FOIL it unless you're really comfortable with the formula, which I'll show you in a second. So what we're gonna do, we'll just FOIL it. So first, grab 3x and multiply. So that 3x times 3x will be 9x squared. So notice both 3 and x has to be squared. Then 3x times 1 is negative 3x. And then you're going to move to the second term, negative 1, and do the same. Negative 1 times 3x is negative 3x. Negative 1 times negative 1 is positive 1. So when you combine it, you get this. So notice it's not definitely 9x squared minus 1 if you were to just square 3x and 1 separately, right, and subtract. This is the correct answer, okay? So you have to FOIL it. And those terms, middle ones, they always are going to be the same repeating. So keep that in mind. Now, what's the formula if you were to square a difference? If you follow this rule, it says, okay, there will be a squared, there will be b squared, but in between there will be product of a and b, because if you were foiling it, you would have to mix them up, meaning multiply a by b. So that's going to, and this ab with negative sign will show up twice. Would FOIL it, right? So it's going to be negative ab. And if you have a sum, so notice what let's go back to this example we did above, just to show you. Now, again, I'm not advocating the formula because I know that leads to too many mistakes. So I would advocate you just to FOIL 3x minus 1 with itself, okay? But if you are curious again how to apply it, then think of it this way. So it tells me, okay, I will have to square 3x and I will have to square 1, except that they're going to be on the kind of outer parts. So I squared 3x and I squared 1. And in the middle will be twice their product. The product of 3x with 1 is 3x. Twice that will be 6x. So if you're comfortable with the formula, you can solve it quickly. But if not, it's just going to take you extra few seconds. Okay? But you'll get there fast enough. Now, if you have a sum, then it's going to be the same, but here will be just all pluses. Okay. So we're going to FOIL A with positive B and so on twice. All right, so let's do one more multiplication. And then we're going to do the division. And I think division you might have not seen before or a long time ago. So I will go through that and probably will continue with division. So remember that we're going to do same as with FOILing. I focus on the first term, x squared, And that one needs to be distributed among both terms from the second parenthesis. So x squared times x and x squared times 3. So x cubed plus 3x squared. Then I'm moving along. So I'm done with x squared. So I'm moving to 2x, next term in line. And I'm going to erase that so you see it more clearly. If you move along, now you focus on 2x. And that needs to multiply both x and 3, right? So 2x squared plus 6x. And once you're done with that, you move to -1, the next one. And again, that one needs to multiply both x and 3. So that's going to be -x minus 3, x cubed plus 5x squared plus 5x minus 3. And then you combine like this. Okay, so how do you feel, guys, about multiplying polynomials? Okay, remember special case squaring, just treat of it as multiplying, right? Just multiply this polynomial by itself, right? And that's how you need to interpret squaring. Okay, next we're gonna go, guys, to a long division algorithm. And let me start with B and then I go back to A because B is kind of unusual. A is kind of unusual, only one term. Okay, so we also have ways to divide two polynomials, but they're not always going to divide evenly, meaning that there's going to be some quotient and there's going to be some remainder, which is the same for numbers. And I'm going to first show you something for numbers so it makes sense. Say, for example, if you wanted to divide 7 by 3, okay? So, or in other words, saying 7/3. First, how many times 3 fits into 7? 2. So that's your quotient. And now what's the remainder? If you fit 3 twice into 7, so that twice 3 is 6. So what still will remain? 1, right? So that 1 is your remainder, which you can write, you have 2 plus, and then this remainder remains, and we cannot divide it by 3. So the only thing we can do is to write it as 1/3, which really boils down to mixed fraction 2 and 1/3. When you do mixed fraction, you do quotient and you do remainder without knowing it, which is really their sum, right? 2 plus 1/3. Why I wanted to show you the example like that for numbers, because for polynomials, we're going to do it in the second, it's going to be the same. If you divide two polynomials, f by g, there's going to be a quotient plus, and then you'll have remainder, which cannot be divided by the divisor by g. So all you can do is to write r remainder divided by g. Right, same for the numbers. Quotient plus the remainder divided by g. Okay, so let me show you the at least one example, and then we'll continue. Let me show you the algorithm for long division. It's called long division. So you write the polynomial x squared plus 3x, and the divisor, so by what you want to divide, you write here on the side. You want to organize both dividend, the polynomial you're dividing, and the divisor from the highest to the lowest power. So that's important. And when you're dividing, you're going to focus on the leading terms, meaning the highest power of x in both. So I'm going to focus my attention on x squared and on the highest power of x in the other, on x squared. So what's x squared divided by x squared? If you don't see it, so this is being divided by x squared. What does it give me, guys? 1, right? So that's 1, and I put it above, right? So what I'm establishing right now, that I can fit x squared plus 2 at least at this point once into that dividend. But then I want to figure out what's the remainder. So what's 1 times x squared plus 2? Well, it's this, x squared plus 2. And that thing now I have to subtract to see what still remains, right? Because I already fitted x squared plus 2 once. So I do basically what that boils down to, this 1. Now we'll multiply x squared and we'll multiply 2. And this polynomial has to be subtracted. And since it will have to be subtracted, what we will do to make things easier, because you will see it's easy to make mistakes, instead of writing this way, I'll distribute the minus. So since this really have to be subtracted, both will have minus now, okay? So you change the sign. So having pencil and eraser is a good idea there. And now since I distributed minus, now I'm just adding them the way I see it. So x squared minus x squared, they will cancel out. 3x and negative 2 are not like terms, so I cannot really combine them. All I can do is to write 3x minus 2. So this is what results when I, from x squared plus 3x, if I subtract x squared minus 2. And some like to kind of, in some textbooks, or sometimes you might like to do it, instead of putting 2 below 3x, you can leave the room and put them on the side, just because they're not like terms, okay? Okay, so now what's left is 3x minus 2. Now, is this a remainder? Yes, because I can't fit x squared in it. So when the power is already less than the power, sorry, if the power is already less than the power of the divisor, then it's your remainder. Where did everything go? So here. So this x is already a remainder because it's less than the power of the divisor. So this is your remainder. And this is your quotient, which tells you that, let me put it in the context what we found out, that we divided x squared plus 3x by x squared plus 2. And we discovered that x squared plus 2 fits once into its dividend, and plus there's still this remainder. And the remainder cannot be divided, so all I can do is to write 3x minus 2 over x squared plus 2. Okay. And you can actually check, because notice that I can write 1 as x squared plus 2 divided by itself, x squared plus 2. And then if I add numerators, they will end up being same as the original fraction, right? So it's quotient plus, and then the remainder over the original denominator. Okay. So let's go back to n. That's all going to be all for today. We'll continue. 3x cubed divided by x squared plus 2x. So 3x cubed, I want to divide by x squared plus 2. And I want to be able to tell what's the quotient and what's the remainder. So it's organized from the highest to the lowest both. And I focus on the highest power of x in my divisor, right? And the highest power, well, here's only one term. So anyway, what's 3x cubed divided by x squared? And you can always write it down on the side. What that will be, guys? 3x, right? Because 2 factors of x will cancel, or you can subtract powers. However you think of it, 2 factors of x will cancel 2 factors of x. So that's 3x. So then I multiply back 3x times x squared and 3x times 2. Because I want to now, we'll want to, if it fits 3x times, then I want to see what it amounts when I multiply by 3x and subtract that to see what's still left to divide. So 3x times x squared, that's 3x cubed. Those should always match. And 3x times 2 is positive 6x. But remember that thing now I want to subtract from the original polynomial. So in next step, that's why I'm marking in red, I'm going to change the signs. It's kind of like distributing the minus, right? Because This way because I'm subtracting. So now those always should cancel out, 3x cubed minus 3x cubed. And then what's left is negative 6x. Okay. And then, well, negative 6x is already my remainder because the power is less than the power of the divisor, right? So that's the remainder. And that's the quotient. So if I wanted, I can write this as the quotient plus the remainder over x squared plus 2. But let's see about this one. X squared minus 2, sorry, x to the power 4 minus 2x squared plus x plus 3. And we want to divide it by x minus 3. So that's then will be, I'm going to write it down, x to the power 4 minus 2x squared plus x plus 3 is being divided by x minus 3. Now I want to say something here that some might teach you that if you have x cubed term missing, you might want to write plus 0x cubed, because you'll see that will just help you a little bit in the initial step of organization. I'm going to point it out to you in a minute. That might be something you might want to do if it's helpful to you. But I don't think it's necessary. So let's focus on the front terms, right? X to the power 4 and x. Okay, so let's divide them. X to the power 4 divided by x. What will I get? X cubed, right? Because it's just lowering the power of x by 1 if you divide by x, right? Okay, so then you multiply back. X cubed times x. So that's going to be x to the power 4. X cubed times negative 3, right? So that's going to be minus 3x cubed. Remember, this one you want to subtract. So now we're going to distribute minus, which will change the signs, right? Okay, so now we're going to have to now combine the two polynomials, meaning add them together, since we already distributed minus. The x to the power 4 terms cancel out, but don't make a mistake of combining those terms, even though they're written below each other, because they are not like terms, right? The power of x differs. So as long as you pay attention to that, that's okay. I'm saying, okay, I have positive 3x cubed term. I have negative 2x squared term. I have positive x and positive 3. Okay. Let me show you something like when I mentioned, because the rest it won't matter, but I told you that some, for the reason of organization, when the x cubed or one of the terms is missing, some like to put 0, because if you did exact same thing, like what we did, basically dividing, then multiplying back, then distributing minus, then the x cubed terms are organized one below the other. So it's, if you feel like you might make a mistake of combining not like terms, like the way we did, now they're organized, so you see that it sums up to 3x cubed, right? So if you like it, do it. But I feel like sometimes there's a lot of terms missing, so putting a lot of zeros, to me, I'm wary of not adding something that's not like terms. So if you feel like you're like that, that's fine. If you're not, then put the 0. But then after that step, you're gonna end up at the same thing, right? 3x cubed minus 2x squared plus x plus 3. The rest would be the same. Okay, so now let's continue, because 3x cubed, so I'm going to continue on the first example. 3x cubed can still be divided by x. And when you do it, you're going to end up with 3x squared, right? Because I'm going to be, after I subtract, I'm going to be continuing to divide by this x, right? And then multiply back. So now 3x squared times x, and 3x squared times negative 3. So 3x squared times x will be 3x cubed. Those should always match. They always should, the leading ones should cancel out. And 3x squared times negative 3 will be minus 9x squared. since this needs to be subtracted, I'm going to distribute minus and now add. So the first cancel out, this is 7x squared plus x plus 3. And then again, I focus on the leading term, the one up front. Can I still divide it by x? Yes, right? It still can fit x in it. If I divide by x, I'm going to get 7x. How are we doing so far? Is it clear what's going on? So then let's multiply back 7x times x and 7x times negative 3. 7x times x is 7x squared. 7x times negative 3 is negative 21x. This needs to be subtracted, so I'll distribute minus. And now when I add, you get 22x plus 3. Now I focus on the leading term. Can I still fit x in it? Yes, right? 22x divided by x will give me 22. And then So on the top, where do you get 3x squared? So which 3x cubed or 3x squared? All on top? Here? Because I divided 3x cubed by x. That was the step when we divided 3x cubed by x, and that gave us 3x squared. Okay, so now 22, let's multiply 22 times x and 22 times negative 3. So 22 times x is 22x. 22 times negative 3 is negative 66. This needs to be subtracted, so we distribute minus, and now we can add, and it gives me 69. And again, I focus on the leading term, but this cannot fit x in it anymore, so that's the remainder, right? And this one is the quotient. And I'm going to leave it. I'm not going to write it in this formula because I think my math lab will ask you just to mention what's quotient and the remainder. Yeah.
So for the negative 7x squared plus 21x, why would it not be negative 21x? It's 7x.
Oh, it was negative originally, but this thing needs to be now subtracted from the polynomial above. So which you can do as well. So if you left it after multiplication, if you left it as it was originally, then think about subtracting 7x squared minus 7x squared cancels out. X minus negative 21 will be plus 21. And it's the kind of experiences for a lot of people that it's easy to make mistake when you have minus. So that's it's better to distribute the minus, so then you're adding, and then it's visually easier to kind of see what it combines to. Yeah. And that's perfectly fine, yes, and that works too. So if you don't want to distribute the minus, then you can just write minus in front and say I'm subtracting. But then essentially you have to know you're subtracting negative 21. You have to make sure you don't make a mistake, right? And I prefer to already distribute the minus. But either way, of course, I'll accept whichever way you feel the most comfortable works for you, will be fine.